Okay, I want to remind you at the beginning of this video that you have a quiz Friday. So make sure you log in and take your quiz and turn in the paper. Okay, so let's look at the subject today, theoretical versus experimental probability. Theoretical probability, you need to know that it is what actually would happen in an experiment. Not that it did happen, but what would if you did do an experiment. For instance, if you were to toss a coin, it has two sides. So the probability of getting one side or the other is 50%, or one out of two. Okay, the next fact, what actually happened in an experiment is the experimental. So that makes sense. This is kind of before you do it, and this is after you've gotten data. So here's some data. A coin was tossed 100 times. Notice this one said if it were tossed. Okay, so let's go back to the experimental. A coin was tossed 100 times. Heads appeared 60 times. Therefore, the probability of the coin landing on heads on the next toss is 60%. So this is theoretical, if you did it, and this is after you did it. So that's what you have to keep in mind when you're answering questions on Friday. Okay. So let's do one. Now, I'm in the classroom. I'm looking over there on the board. We had some students who did this. So what I'm going to do is record what they did. So again, I'm looking away on the board. So again, someone did this, and they rolled a 1 on the die 9 times. They rolled a 2 12 times. They rolled a 3 4 times, and then 7, 15, and 13. Okay, so I'm going to add that up real quick and make sure it equals 60. Okay, it says it equals 60. Let's see, 16, 23, 32, 42, 52, 53, 54, 55, 60. Okay, so that equals 60. And it should, because they were told to flip the coin 60 times and record the data. Okay, so let's go through this. Now, again, this says theoretical. I'm going to do that in green, and this says experimental. Theoretical is without the data. One more time, without the data. Theoretical is just with the die. What is the probability that the next roll is an odd number? So I'm going to think, how many odd numbers on a die? There are 3, 1, 3, and 5. And how many total numbers are there? Are 6.
Joanne Miles, please report to the front office. Joanne Miles, please report to the front office.
Okay, and if you were to divide 3 and 6, the first 2 digits are 50. Or actually, the first 2 digits are a 5 and nothing, so I know that is 50%. 0.05, in other words. What is the probability that the next roll is a 1 or a 4? Okay, so on this die, how many 1s, how many 4s? Well, 1 of each. So I'm going to say 2 out of 6. In fact, all these are out of 6 because, again, this is before you roll it even once. Okay, if you divide 2 and 6, you would get a bunch of 3s repeating because this is 1/3. So I'm going to put 33 and 1/3%. Okay, now if you need refreshing on this, go back to yesterday's lesson or the day before, okay? What is the probability that the next roll is at least 2? Okay, so at least 2 means the littlest is 2. So 2, 3, 4, 5, 6. So that's 5 numbers. So we're going to 5 here. And when you divide that out, you're going to get 87.875. So I'm going to call that 87.5%. Okay, now notice this little round to hole. We're fixing to use this. Okay, out of 100 rolls, and now notice these ask the probability. Probability, probability, probability. But this says about how many times would you expect to roll a 3. Okay, so we're not looking for percent. We're not looking for probability. We're looking for how many times. Okay, would you expect to roll a 3? So I'm going, if you rolled it 100 times. So I'm going to make a fraction here, and right now, hang on, I was good. Change that to green. Okay, out of 100 rolls. So over here, I have, this is out of 6, and there's only 1 3, but I want to know how many times would that translate to 100 rolls. So I'm going to write 100 under there. Okay, and I'm going to put a T here for 3. So when I get an answer, that's how many 3s I would roll out of 100 if I would roll 1 out of 6. So we're going to cross multiply and divide, and you end up with 16 point something. So I'm going to put T equals very small. I'm going to round up to 17, and that's 3s. You would roll 17 3s, that's apostrophe, if you were to roll 100 die. So that is my answer. Now I rounded to the whole place, because when you roll a die, you don't get part of an answer, you get a whole answer. So that's why this little note is out here, round to the whole. Okay, let's go with blue for this one. Experimental probability. Now we need my data. Okay, so experimental means you did the experiment and now you need the data. So let's answer the same questions, but with this experimental data. What is the probability that the next roll is an odd number? So I need the number of odds. I'm going to add 1 plus 3 plus 5. And okay, I'm going to actually have to do that. I'm going to borrow my calculator. Okay, 9 plus 4, I could have done this in my head, I think, plus 15, and I got 28. So 28 times and then out of, we spun the die 60 times, so that's going to be the bottom number. In fact, it's going to be the bottom number for all 3 of these. Okay, and down here. But remember, I'm finding out of 100. Okay, so 28. So I'm going to take my handy dandy calculator and say 28 divided by 60, and it's 0.46 repeating. So I'm going to say 46 2/3%. Okay. Now, what is the probability that the next roll is a 1 or a 4? So I'm going to add the 9 and the 7, which is 16. Okay, handy dandy calculator. 16 divided by 60 is 0.26 repeating. So this is going to be 26 2/3%. Okay, next one. What is the probability that the next roll is at least 2? So that means I'm going to add up the 2s, the 3s, the 4s, the 5s, the 6s, or I can say 60 minus 9, because we're counting everything but the 1s. So I'm going to make this 51. Okay, handy dandy calculator. 51 divided by 60, and it's 0.85. So I'm going to move the decimal twice and make that 85%. Okay, next. Okay, now hopefully you're noticing 50 and 46 aren't the same. 33 and 26 aren't the same. 87.5 and 85 are not the same, although they're close, but they are not the same. So just kind of keep that in your mind. Okay, what do we want? Our favorables. Out of 100 rolls, about how many times would you expect to roll a 3? So let me look back at my data. How many 3s out of that small sample? 4. So I'm going to assume to continue, and this is out of 100. And so I'm going to say 4 times 100, which is 400, and then divide by 60. 400 divided by 60. 6.6 repeating. And remember, we're rounding to the whole number, so I'm going to say 7. Oh, and by the way, you were expected to find 3s, so I'm going to say T equals 7. Because again, I rounded up to the nearest whole place, 3s. So I would, if this pace continues, I would expect to roll 7 3s out of 100. Okay, now let's look at these questions. They're pretty important. Do the theoretical results match the experimental results? Okay, I'm going to say no. They don't match exactly. They're close, some of them, but the answer is no. And normally real world stuff is not perfect. So to me, this is kind of in the perfect world, and this is in the real world. How could the experimental results get closer to the theoretical results? Well, I talked about casinos. Okay, did you know that a casino owner, when you walk in the door, or you're adults who go to gamble, they actually see them as losers, okay? If they didn't, if people won all the time and they won too much, casinos would have to close their doors. They couldn't make money. So guess where they make that money? Off of several things, but the biggest part of their money is when you lose, when you gamble. Okay, so, but let's say 5 people walked in and 5 people hit a jackpot, the jackpot. Well, they know, well, we got to keep on going, because at some point people are going to start losing, and they'll lose every day. More people will lose every day above winners. Again, if the winners always exceed the losers, they're going to have to close their doors. So know that when you walk in, the odds are against you, otherwise they couldn't stay open. So how do, if they've lost to those 5 jackpot winners, if they've lost, what do they have to keep doing? They have to keep going, and we're going to say out to infinity. So think of infinite number of customers walking in, gamblers walking in. At some point, they're going to start losing money, and the casino will regain their money. So the question is, how could the experimental results get closer to the theoretical results if you keep going to infinity? They will start looking the same, okay? Okay, so now I'm going to scroll down. Do you see these 4? The 4 starred problems are like what you will have Friday, okay? So we want to definitely pay attention to those, but these are practice up until then. Okay, what is the theoretical probability of choosing a C? Now again, this is what you want to think about. You don't want to think about this results because this quote unquote hasn't happened yet. Theoretical is before you get the frequencies. A letter in the Word Excel is chosen 50 times. Results are shown in the table below. Okay, we want to ignore this. This says theoretical, this says experimental. So I'm going to put a fraction here, and we want to know the probability. So we're looking for percent. Now, if again, if I cover this, Excel, ACCEL has 5 letters. Now, how many times could you choose a C? Well, if there are 5 letters and 2 of them are C's, it's 2 over 5. Okay, and then I'm going to divide that out on my calculator, and that is 40%. Okay, there's your answer. Okay, now what is the experimental probability of choosing that C? So again, should be 50. Okay, they chose 50 times out of that bag. In other words, they put them all in, they chose one out, and they put it in, shook it up, and chose again. Put that one in, shook it up, chose another letter. So there were always 5 letters in there when they were choosing. Okay, what is the experimental probability of choosing a C? Okay, well, let's look. Do you see 5 and 7? So if I added 5 and 7, I would get 12. Okay, divide that out, and you get 0.24, which is 24%. Okay, going on. Different type of data. Again, we have that word theoretical, and we have the word experimental. So again, I'm just going to kind of block this out of my mind. I'm not going to think about it. The spinner to the left is spun 80 times. Again, we're going to stop because that information goes with B. Okay, so let's draw a fraction bar, and we want to know the probability of not landing on polka dots. Okay, there are 2 polka dots, but how many spaces total? 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 spaces total. Since 2 are polka dot, I'm going to say that 8 minus 6 is 2. Excuse me, 8 minus 2 is 6. So there are 6 non-polka dot spaces. So if I divide that out, now I know that's 3/4, and I have that memorized at 75%. Okay? Okay, experimental. So now we need this. How many total? 80. And we want to know what is the probability of theoretical probability of not choosing, experimental probability of not choosing polka dots. So I'm going to add the stripes and the solids, which is 62. 62 out of 80, and divide that out and you get 77.775, so that's 77 and a half. Okay, now the rest of it says, compare this to the theoretical probability. Okay, do you see? Compare. 75 and 77 and a half are not the same, but they're close. Okay, so we're going to go on. Okay, so these are different. Let me just kind of flash these two here first. Let's read. A day of the week is chosen at random. Forget the 40 right now because, again, we're on theoretical. And next we'll do experimental. Okay, so let's read the theoretical. If a day of the week is chosen 150 times, okay. Remember, this is before they did all this. How many times would you expect a day that starts with the letter T? So I'm going to put a T up here. That's what we're looking for. Remember, round to whole. Because we are not looking for probability, we're looking for how many would you choose. Okay, theoretical. Now, out of 7 days, how many start with the letter T? 2, Tuesday, Thursday. So cross multiply and divide, and T comes up to be 43 because I round. 43 days with beginning letter of T, okay? We're just gonna abbreviate that. Okay, next one. Now we're gonna pull in this data and use it to answer our question. Based on the experiment, if a day of the week is chosen 150 times, how many times would you expect a day that starts with the letter T? Oops, I don't know how I did that, okay. So let's put this here. Out of 150 days, we wanna know, but again, this is out of our experimental data. So how many total? We had 40. And how many were two? Okay, Tuesday is 2, Thursday is 8, so that's 10. So you're going to cross multiply and divide, and T equals 38. Again, because we're rounded to the whole. 38 days that begin with T. With T, okay? Okay, last two. Again, theoretical, experiment. So disregard this, read this. A small deck of cards has 4 kings, 3 queens, 2 jacks, and 1 ace. Okay, I had folks just go straight ahead and they put a 4 here because they saw 1, 2, 3, 4. But that was wrong because you didn't just have 1 king, you had 4. I mean, that is lying on the table. That's before you chose at random. So I'm going to stick a 4 here, a 3 here, a 2 here, and a 1. And how many cards are on the table? 4, 5, 6, 7, 8, 9. There are 10 cards on the table, so that's how many you have to choose from every time. Now they want to know how often would you, if you drew 1 time, how many times would you draw an ace? And it's 1 because there's only 1 ace card. So what is that? It is. Now they want to know if you drew out of 200 cards. So I'm going to say 1 times 2. Oh, by the way, I'm going to put an A for ace. So when I finish, that's how many aces you would draw out of 200. Okay, 1 times 200 is 200, and divided by 10 is 20. So I'm going to put 20 aces drawn. Okay, last question. Now, based on his experiment, okay, so let's draw on this data. 75. And we're going to make 200 draws. So how many aces did he draw? 12. So cross, A for ace. So 12 times 200 divided by 75 rounds to 32. 32 aces drawn. Okay, don't remember you should have written this on paper and attach pictures and turn in for your attendance grade. Okay.